Hello, everyone. In this video, we're going to continue our work in section 8.1 of the workbook by looking at example 2. All right, in this example, we're going to learn about a different sequence and observe its behavior. So this sequence, or in this example, rather, we're asked, suppose that the population of fish in a lake after n years is modeled by the formula P sub n is equal to 1002 e to the n over 3 e to the n plus 164. A portion of the graph of the sequence P sub n is shown to the right. So just to understand that graph a little bit here, when n is 0, that P sub 0 is going to be around here on that vertical axis. When n, so these are the n's like it says, when n is 1, P sub 1 will be up here, etc. So each point here on the graph represents the year and the P sub n associated to it. Okay, so for part A, it says find the values of P sub 0 through P sub 4. What do these numbers mean in the context of this problem? So first of all, let's take care of that first part of the problem where we want to figure out the values P sub 0 through P sub 4. So we could even set up a table here. So I'm going to use n and P sub n, and we're going to fill in this table for 0, 1, 2, 3, and 4. You'll make sure I'm giving myself enough room. 1, 2, 3, 4. And we'll find those P sub n values associated to each n. So let's just do a couple together, and then I'll have you finish the rest. So first of all, P sub 0. So for P sub 0, we're just going to plug in 0 wherever we see n in that formula for P sub n. So that's going to look like 1002 e to the 0 over 3 e to the 0 plus 164. So that becomes 1002 over 3 times 1 plus 164, which we can then consult our calculator and we get 6. So in year 0, we'd have 6 fish. All right, that was so much fun. Let's just do one more together and then I'll have you finish the rest. So P sub 1, we're just going to plug in 1 wherever we see n. So we get 1002 e to the 1 over 3 e to the 1 plus 164. All right, so we can just put all of that in our calculator. It becomes a little messy, but nothing our calculator can't handle. So 15.8 is what we get. So we should have 15.8 fish, which we don't have to round. We're not too concerned about the specific context here. We're just trying to get a sense of these numbers. All right, so now I want you to pause the video and finish filling in this table on your own. And when you're ready, you can compare your answers to what I computed. All right, so for n equals 2, we should be getting 39.8. For n equals 3, we should be getting 89.7. For n equals 4, we should be getting 166.9. Okay, so that takes care of these first P0 through P4 values. But now what about the second part? What do these numbers mean in the context of this problem? So what we are computing are these P sub n's, which what are those values? Well, we are told that is the population of fish in the lake after n years. So then we can summarize that each value in P sub n is not specifically the number of fish because we don't have a seventh of a fish or 7/10 of a fish rather, but is an approximation of the number of fish in the pond after n months. Oh, does it say months or is it years? Let's look back. What is n? Years. So this should be n years. Fish don't grow that fast in this pond, I guess. All right. But again, the focus here, this sequence approximates the number of fish in this pond. All right, so then we could ask a similar question as the first example we saw and ask, well, what happens to, or what is the behavior of these P sub n's as n gets larger? Well, so far what we've seen is that as n increases, Pn increases. And we see that here in the graph too. So we might be left to think that, well, the fish are just going to continue to increase in population forever. Well, part B of this question asks, does the sequence P sub n converge? And if so, to what value? So before we can just say, yes, it converges, we've only looked at 5 values here. So this doesn't give us a really big picture of what this sequence does in the long-term behavior. So we should definitely be looking for more than 4 when we're talking long-term behavior. And in fact, if we look at some more of these values, so I'm going to actually graph a little bit more of what these values should be looking like. So if I have our graph here, I'll set up some axes. So rather than just going to 4, I'm going to go a little larger. Okay, so rather than just going to 4, I'm only going to go out to 8. So not too crazy. 2, 4, 6, 8. But I'm going to give us a little bit more sense of this sequence or what happens with these numbers. So you can graph this on your own using Desmos. In fact, I encourage you to do that. And what you'll see, and in the graph of Desmos, you'll get a smooth line here. But we only care about those P sub n values when n is an integer. But what you'll see is that, yes, we have this behavior here, kind of like this, up until 4. But then what starts to happen is our graph kind of levels out, which makes us wonder then that maybe these values do converge. So how do we determine the convergence of this sequence? Well, we can set up a limit just like we've done with functions. So we can consider the limit as n goes to infinity of P sub n. So that's going to be for us the limit as n goes to infinity of that 1002 e to the n over 3 e to the n plus 164. So now what happens when n blows up? This exponent blows up, gets larger and larger. Well, we see that that numerator is going to blow up, go to infinity, but also the denominator will go to infinity. So you might recall from Calculus 1, maybe a long time ago, that when we're in this situation where we're considering a limit where the function or the limit goes to infinity over infinity, then we use something called L'Hopital's rule. I'm going to denote it by an H. So that H means we're using L'Hopital's rule. And what that rule says is that to compute your original limit, it's the equivalent question to compute the derivative of the previous function. The limit of that previous function using the derivative of the numerator divided by the derivative of the denominator. So what does that look like for us? Well, the derivative of that numerator, we have derivative of 1002 e to the n. So the derivative of e to the n is just e to the n. So we just get 1002 e to the n. The derivative of the denominator, 3 e to the n, would just be 3 e to the n again. But then the derivative of a constant is just 0. So we're just left with the limit as n goes to infinity of 1002 e to the n over 3 e to the n. Okay, well, what can we do with that? Well, we can recognize that there's an e to the n in both the numerator and denominator. So those values actually cancel out. So we're just left with the limit as n goes to infinity of 1002 over 3. And now this is no longer involves an n. So as n increases, our values here just remain the same, this constant number. And if we compute that in our calculator, we should be getting 334. So this sequence of P sub n's actually converges to 334. So let's go ahead and write that down. So the sequence P sub n converges to 334. So what does that mean in context? So that means the fish population, approaches 334 in the long run. So if there was no other interventions or other predators introduced into the pond, then eventually the population of fish in the pond would just level off. And that leveling off would end at around 334. So it would just get to around that population and then stay that way. Awesome. So here in this example, just to recap, we saw this sequence that represented the population in a pond over n years. When we analyzed that sequence and dug further into its behavior, we saw that that sequence actually converges to 334. Awesome. Thanks so much for watching.